Thanks very much, and thank you also to the organisers for the opportunity to speak to you today. So, yeah, in the context of the current workshop, I suppose my interest in this talk is on the energy exchanges between quantum systems and their external control fields. In particular, I'm interested in the statistics of work exchanged in such ways, so going beyond just looking at the averages of those energy exchanges. And ideally, I'd like to consider systems where, so this quantum system is embedded in some surrounding environment, and we don't necessarily treat that environment as weakly coupled to the system as we might do in a kind of textbook setup. So that's the kind of context for the talk. So actually the motivation originally was just curiosity about strong coupling thermodynamics and how we incorporate system-environment interactions more explicitly into the thermodynamics of quantum systems. So as I mentioned, I'm going to focus on calculating the full work distribution for a driven open quantum system. So let's see if this works. No, I've turned it off. No, I've made it disappear. It's back. Yeah. No, I was trying to get the laser pointer.
Oh, laser point in the middle.
Yeah. Can anyone see that? Doesn't matter. Okay, so I'll try and not make that disappear again. So we've got some system. It's embedded in a surrounding environment. And we're assuming some external control of the system, so it couples to the system degrees of freedom. But of course, if the system is interacting with the surrounding environment, it's the full system plus environment that's going to exchange energy with that external control. Now, the full system plus environment, I'm going to assume evolves unitarily, so I'm going to use that to characterize the work in the energetic exchanges. Of course, trying to determine the statistics of work in strong coupling regimes from a full system environment model is going to be quite a formidable task because it would require essentially a calculation of the full eigenspectrum of the system plus reservoir. But we're going to circumvent this issue here using some unitary transformation, so namely a polaron transformation that's going to allow us to incorporate some of the strong coupling physics directly at the Hamiltonian level. And we'll apply it to a simple Landau-Zener protocol just to see how this works in practice. Okay, there are a number of different ways we could characterize the stochastic work in such a process, but I'm going to look at a two-point measurement protocol just for something concrete. So how does this work? So we consider projective energy measurements performed, as I said, on the combined system plus environment, and that's closed, so it involves unitarily. So we're going to use the outcomes of those energy measurements to describe the work that's done on the system. So let's assume we have a combined system and environment in some initial state rho 0. It could, for example, be a global thermal state of the composite, and we make some energy measurement. Now this is not straightforward experimentally, of course, but as a theoretical construct, let's consider it to characterize our work statistics. So we make some energy measurement at the initial time, we get some output, epsilon n, and there's some projector onto that energy eigenstate pi n. We allow the system to evolve unitarily over some time scale t, and then at the final time we make some other projective measurement of the full combined system and environment energy. That gives us an outcome epsilon m at t with a projector onto the associated eigenstate pi m. So how do we construct a work probability density from that? Well, the probability of getting the outcome n in the initial measurement is given by a trace of the projector with the initial density operator, and then the probability of getting outcome m at time t, given that we got outcome n at time 0, is just given by projecting the initial state and then unitarily evolving it, and then tracing that with the projector onto the final energy eigenstate pi m. and then we can normalize that by the initial probability Pn. And so if we sum over these probabilities, over all possible outcomes, and then associate the work with the energy difference between the eigenvalues we get, the energy eigenvalues at those two times, we can construct the full work probability distribution for our energy exchanges of the system and environment with the control field. Now actually, it's not particularly convenient to work directly with the work probability distribution. We can't really sum up over all those possible energy outcomes when we've got some system coupled, for example, to some large continuum bath. So for practical purposes, it's easier to work with the characteristic function, which is the Fourier transform of the work probability distribution. And the reason for this is we can formulate the characteristic function calculation in terms of an open system dynamics, and so we can use open quantum systems theory to calculate this characteristic function and then get the work probability distribution by inverting the Fourier transform. So the characteristic function then contains all the same statistical information about the work performed on our system plus environment, and we can get work moments by taking derivatives of the characteristic function if we want to. And what's important is the characteristic function itself can be written as a trace over something that's like a generalized density operator. So it's a density operator that depends on what I'll call the counting field. So this is the variable chi that appears in the Fourier transform of the work probability distribution. We can split that trace into a trace over the environment first, so a trace over the bath to define a reduced counting field dependent density operator rho s, and then we would trace over that the system degrees of freedom to get then the characteristic function at the end. Now notice that the characteristic function itself, as it's written in terms of a trace, I can put any unitary transformation I want inside that trace and I don't change the overall quantity. And that's what I'm going to use in the end to go beyond weak coupling. So I'm going to transform the density, the generalized density operator by this polaron transformation to a new representation where I'm perturbing instead not in the system environment coupling strength, but in fluctuations around this polaron-like representation, which for certain systems is a much better perturbation theory to explore. I'll say a bit more about that later. So we now construct our formalism much in the same way as we would construct master equations for open quantum systems theory. So taking the derivative of the counting field dependent density operator, we get something that looks like a bit like the Liouville-von Neumann equation, although note that we don't have a commutator on the right-hand side because the sign of the counting field changes in the second term in the Hamiltonian. The Hamiltonian itself is transformed, so it's time dependent because we're driving the system with some external influence, but it also has an extra term on the right-hand side there, which comes from trying to track the work exchanges between that driving field and the system. If we go through the usual process of deriving a master equation within Born-Markov-like approximations, we'll end up with a generalized master equation once we trace out the environment, which has a generic form that I've given there. So it determines the derivative of the system density operator or generalized density operator in terms of some Liouvillean that itself depends on the counting field and time, because we're explicitly time dependent here, and the density operator at the current time t. Now the actual form of that Liouvillean, so the equation I've given there is fairly generic, but the form that we get in practice depends on the approximations we make in the derivation, of course. So a standard kind of textbook Born-Markov approximation would apply only to very weak coupling between the system and its surrounding reservoir. But as I said, we're going to try and go beyond that through this polaron approach. For simplicity, we're going to assume slow time dependence here so that the system is only driven adiabatically, but actually there are a number of techniques that we could use to go beyond that slow driving limit as well. Okay, so I've mentioned this polaron transformation a couple of times. And if you're not familiar with it, you might be wondering why I might be wanting to use that approach. Well, actually, the reason is that it's very well justified in certain solid state systems. For example, optically excited quantum dots, so semiconductor nanostructures, which themselves are interesting candidate systems that are often explored, well, quite intensively explored for quantum technology applications. So if we imagine we've got some semiconductor nanostructure and it's in its ground state, so that's, you know, full valence band in terms of the electronic states, the lattice that surrounds it, so you know, it's in some solid and it's fabricated in some solid, some gallium arsenide material, for example, and that lattice is in some equilibrium with respect to that initial state. Then we excite the system with some external field, and we excite an electron then out of the valence band to the conduction band. The charge configuration changes as a result, and the lattice ions then want to change with respect to that new charge configuration and try and equilibrate instead with the new charge configuration, and that gives rise to a displacement, as you see on the right-hand side. And if I excite, for example, Rabi oscillations of this system, the lattice is going to try and displace when the system's in the excited state and then displace back to its original equilibrium when the system's in the ground state, and so on as I excite it between different states. And in systems such as self-assembled quantum dots, we know that this process is one of the dominant processes in the strong coupling and non-Markovian physics that's seen in such systems. And so we want to incorporate this representation into our treatment directly at the Hamiltonian level. So what we do instead is we perturb around fluctuations around these equilibrium states rather than in the system bath coupling strength itself. So that's fluctuations around the displaced equilibria. The way we do that is via a unitary transformation. And as I said, it allows strong electron-photon couplings in these kind of systems. What's nice is because we maintain a master equation approach, we can quite easily continue to obtain direct experiment theory comparisons. And this actually confirms that the polaron treatment, the polaron way of looking at these things, is an accurate way of modeling such real systems. So this is some data from an interference experiment that was done in Sheffield, and you can see that on short time scales here, there's a short time loss of fringe contrast in the signal before a much longer time scale decay of fringe contrast due to Markovian loss processes. And that short time loss of fringe contrast is a non-Markovian signature due to this precisely this polaron formation. And we can see that the polaron master equation approach very well captures the experimental data here, whereas a standard kind of Markovian decay does not capture the initial loss of fringe contrast. Okay, just to say on a technical level, we apply this transformation to the Hamiltonian. It looks like a displacement of the environmental oscillators, but the displacement is dependent on the population difference operator of the system, so whether the system is in its ground or excited state. And that leads to, importantly, renormalizations of the system Hamiltonian quantities. So if I have a very standard Landauer-Zener-like system Hamiltonian, where I've got a linear ramp of the splitting, the bias between a two-state system with some tunneling delta, splitting those two states when the bias is zero, then the tunneling gets renormalized by this parameter kappa due to the polaron transformation. So it actually reduces the tunnel splitting in this situation. And so we follow now a standard adiabatic Markovian procedure in the polaron frame to obtain a generalized master equation as before. But even though we've applied still the standard Bohr-Markov approximations, we've done them in this transform frame. So we're not limited actually to weak coupling dynamics any longer. Let me just benchmark that. So this is looking at a Landau-Zehner process where I'm starting the ground state and I'm trying to slowly go through some anti-crossing, but of course there may be some non-adiabatic excitations because I'm going at finite rate, and there may also be phonon exchanges, interactions that take us between the ground and excited state. In the top left-hand corner, I'm looking at weak coupling. I'm comparing, well, the main curves to look at are the blue dashed line. That's some numerical benchmark for the dynamics, where I can numerically capture these dynamics, but not the work counting statistics. The green lines are the Polaron-Master equation, and the red lines are a weak coupling approach. At weak coupling, everything agrees, but as we see, as we increase the coupling strength on the right-hand side, or both the coupling strength and the temperature on the bottom right-hand side, the weak coupling approach starts to disagree with the benchmarks, but the Polaron-Master equation still very well captures our dynamics. So we're confident then that we're capturing these non-perturbative aspects. So I've only got a couple more slides and then I'll finish. So here's the full work distribution from these two approaches, either the standard weak coupling approach, which we believe breaks down, and the Polaron-Master equation approach, which we believe to be accurate in the strong coupling regime. You can see a number of different peaks in the work distribution, as well as a general broadening of the distribution towards larger work values. I'm doing work on the system here. I'm driving it from the ground state and ending up in the excited state if a Landau-Zehner transition or a phonon absorption occurs. And the different peaks are labeled by the processes that we see on the right-hand side, just to give some kind of physical context to what's happening there. Importantly, we can see that because it's a log scale on the vertical axis, the weak coupling approach underestimates the probability of some of these processes by orders of magnitude. So just finally to say that perhaps more interestingly, as we change the system environment coupling strength, or indeed the temperature of the system similarly, we see that the peaks shift in the Polaron-Master equation approach. And this is because, as I said, we get renormalizations due to the strong coupling physics between the system and environment of the system energy scales. And so actually the work values that we obtain are renormalized by the system environment coupling. Now this is completely missed by the weak coupling approach, where we see all of the peaks lying on top of each other regardless of the system environment coupling strength. Okay, just to summarize, I've shown you an approach to look at the full work probability distribution beyond weak coupling between some system and environment via a Polaron transformation approach. There's a number of open questions and extensions, particularly how we probe these work distributions experimentally. So I'll just finish by thanking my collaborators on this work and you for your attention.
So are there any questions?
Hi, thanks for the nice talk. So after doing this Polaron transformation, do you have a condition on the spectral density of the bath for to have a weak coupling, to be able to apply weak coupling assumption afterwards?
So for the standard Polaron transformation, superohmic spectral densities are most convenient. They're also what's most applicable, for example, to phonon interactions in solid state systems. There are ways to go beyond that. So there's ways to optimize the Polaron transformation for other spectral densities using a variational type approach. But also we could apply different transformations, so I can put any unitary in there I want. And so it could be, for example, that I apply a different type of mapping. A reaction coordinate or a chain type mapping, for example, would also work and would allow us to capture different kinds of spectral densities in systems as well.
Yeah, thanks.
Other questions?
Thank you for the beautiful talk. My question is, I'm trying to understand, so you are doing a generalized like strong coupling master equation for the, like a reduced state connected to the work distribution function, right? Does it say anything about the dynamics of the system itself? How does it relate to the like dynamics of the system beyond Markovian?
Yeah, it does actually. So we're using the same master equation to calculate these dynamics in the benchmark here. It's just if we set the counting field chi to 0, that gives us then the system dynamics rather than the work distribution. So we can consistently get the system dynamics out of the formalism as well as the work probability distribution. So that's how we did our benchmarking here. We set the counting field to 0 and we compared with the numerics that come out of this method that's known as tempo in the literature. Now the tempo method itself, we can't apply to the work distribution, at least not at present, which is why we had to look at different ways to go about that.
Okay. Thank you.
Any last question? So thank the speaker again. And,